Hi, good morning. Just recall what we have discussed in our last class. We have proved LVW is a vector space. Also, we have proved the dimension of LVW is Mn. Now, we are going to prove another theorem. The theorem says that let V, W and set be vector spaces over the field F. And let T be a linear transformation from V into W. And U a linear transformation from W into Z. Okay, T is a linear transformation from V into W and U is a linear transformation from W into Z. Then the composite function ut defined by ut of alpha equal to u of t of alpha. This is just like our composition function. Ut of alpha equal to u of t of alpha is a linear transformation from v into z. Okay, we have to prove this composition function is a linear transformation. Last class we have proved sum is a linear function, also scalar multiplication is a linear function, linear transformation. Okay, so here we have to prove this composition function is a linear transformation. Now look at into the proof. Given T is a linear transformation from V into W and U is a linear transformation from W into Z. Okay, then UT is a composition function from V into Z. UT is a UT is a transformation from V to Z. Now we have to prove this UT is linear. Okay. Now what is actually UT? UT is defined as U of T of alpha. Okay. So to prove UT is linear, we have to prove U of UT of C alpha plus beta equal to C into UT alpha plus UT beta. Okay, that's what we have to prove. To prove UT of, we have to prove C A alpha plus beta is equal to C UT of alpha plus UT of beta. This is what we are going to prove. Okay, now you consider this. Now using the definition, this is U of T of C alpha plus beta, but T is a linear transformation. Therefore, T of C alpha plus beta you can write as C T alpha plus T beta. Now U of, okay. So you can write like this. U is also a linear transformation. So U of C T alpha plus U of T beta. And U of U is a linear transformation. U of C into something. Okay, that's equal to C into U of T alpha plus U of T beta. Okay. And from this U of T alpha you can write as UT of alpha and U of T beta you can write as UT of beta. Okay. Thus we get UT of C alpha plus beta equal to C into UT alpha plus UT beta. This implies, this is true for every alpha comma beta belongs to V. This implies UT is a linear transformation. Clear? Now, here we have the spaces V, W, Z. Okay. There may be cases like V equal to W and Z also equal to V. Okay. In such a cases, the linear transformation is called linear operator. This is what our next definition. If V is a vector space over the field F, a linear operator on V is a linear transformation from V into V. Okay. And we denote LVV, the space of all linear operators on V as LVV. Space of all linear transformation from V to W is LVW and set of all linear transformation from V to V is LVV and this linear transformation from V to V is called linear operator. Therefore, LVV is the space of all linear operators on V. Okay. Now there is another note. If V equal to W equal to Z in the above theorem, then UT and TU are linear operators on V. In general, UT is not equal to TU. Okay. Suppose we have T is a map from V to V. And because V, W, Z are equal. Okay. And U is a map from V to V. Therefore, ut is a map from V to V defined as ut of alpha equal to u of t alpha. This is a linear transformation we have already proved. Now, what is the map tu? Tu is again a map from V to V. And tu of alpha equal to t of u alpha. We can easily prove tu is also a linear transformation. And we have to prove, we have one result. In general, ut is not equal to t. That means in general, this composition operation is not commutative. For proving this, we are looking at one examples here. Example is very easy. Let f be a field and v be the space of all polynomial function from f into f. Okay. Let d be the differentiation operator that we have already discussed, and t be a linear operator on v defined by t of f of x equal to x f of x. Okay. You can easily prove this t is a linear map. Okay. And t is defined as t of f of x equal to x f of x. Now, what is dt and td? If you look at td of f of x equal to, by definition, this is t of df of x. And this is equal to t of df of x. You can write as f dash x, derivative. Okay. And tf of x is x f of x. Therefore, tf dash x is x f dash x. Okay. Now, what is dt of f of x? dt of f of x is d of t of f of x. But t f of x is x f of x. Therefore, derivative of x f of x. Here we apply product rule. That means x into df of x, that is f dash x, plus f of x into derivative of x. Therefore, x f dash x plus f of x into derivative of x is 1. That is x f dash x plus f of x. So here we have td is equal to x f dash x and dt equal to x f dash x plus f of x. Clearly, td is not equal to dt. Okay. Now, what is dt minus td? One more question is there. Find dt minus td. Check whether td equal to dt. The answer is no. Okay. Now, find dt minus td. Now, dt minus td of f of x equal to dt of f of x minus td of f of x, that is x f dash x plus f of x minus x f dash x, and which is equal to f of x. F of x you can write as I of f of x. Therefore, dt minus td equal to I, the identity operator. Okay. Now, if t is a linear operator on V, then we use the notation t square for tt. And we use the notation t cube for t square t and or t square, and this is actually t. Now, in general, t raised to n you can write as t etc. t n times. Okay. So, using above theorem, ut is a linear transformation. Similarly, tt is a linear transformation. Therefore, t square, t cube, t raised to 4 etc. tn are linear operators on V. Okay. And we can define t raised to 0 equal to I. We can define t raised to 0 equal to I if t not equal to 0. That is, if t not equal to 0, we define t raised to 0 as identity transformation or identity operator on V. That is, I of alpha equal to alpha. Now we are going to prove one lemma. Now what is lemma? All these things are very simple. Let V be a vector space over the field F, U, T1, T2, etc. be linear operators on V, and C be an element of F. Then we have to prove these three conditions. IU equal to UI equal to U of T1 plus T2 equal to this one. Here, this condition also. CU T1 equal to CU T1 equal to UC T1. Okay. Now, what is IU of alpha? IU of alpha equal to IU of U alpha. I is an identity map. Therefore, IU of U alpha is U alpha. IU of alpha equal to U of alpha for every alpha belongs to V. This implies IU equal to U. Now, we have to prove UI is equal to U. Now u I alpha equal to u of I alpha. But I alpha is identity map. Therefore, I alpha is alpha. This is equal to u of alpha. Thus, we get u I of alpha equal to u of alpha. And this is true for every alpha belongs to V. This implies ui is equal to u. Thus, we get iu equal to ui equal to u. Thus, we have proved the A part. Now, looking into B part, we have to prove ut1 plus t2 equal to ut1 plus ut2. For proving this, we have to prove this condition hold for every alpha belongs to V. Therefore, consider u of t1 plus t2 of alpha. Why we are looking at these types of problems? Here, all these are function. Okay, f equal to g only if f of x equal to g of x for every x in the domain. Okay, therefore we are proving this of alpha equal to this of alpha for every alpha belongs to V. Okay, therefore we are taking some arbitrary alpha belongs to V, and this of alpha equal to, by definition, this is u of this one. But this is t1, t2 are linear, therefore you can write like this. This is actually a definition. Okay. Now, this is actually already we have discussed in last class. T plus u of alpha equal to t of alpha plus u of alpha. Okay, u of alpha. Now this is okay. Now u is linear map. Therefore, this you can write like this. And this is actually ut1 of alpha, and this is ut2 of alpha. Therefore, ut1 plus ut2 of alpha. This implies, and this is true for every alpha belongs to V. Therefore, this. Now, similarly, you can prove t1 plus t2 of u of alpha equal to this one. I am skipping this proof. Okay. This is very easy to prove. Okay. Now, moving to last, that alpha belongs to V, we have to prove CUT1 equal to CUT1. C into UT1 alpha is equal to, by definition, we have CT of alpha. Scalar multiplication is defined as C of T alpha. Okay, therefore this you can write as C of UT1 of alpha. And this you can write as C of U of T1 of alpha. Okay, CT of alpha you can write as CT of alpha. Therefore, C into U of something you can write as CU of that something. Okay, and which is equal to CUT1 of alpha. And this is true for every alpha. Therefore, CUT1 is equal to CUT1. Now let alpha belongs to V, and we have to prove the last one. U of CT1 of alpha is equal to U of C1 of, okay, this of alpha. U of ut of alpha is equal to u of t alpha. Okay, similarly u of c1 t1 of alpha is u of c1 t1 of alpha, and this is actually u c t1 of alpha. And as u is also linear, this you can write as cu of t1 of alpha, and that is same as cu of t1 of alpha, and this is same as some u of t of alpha is same as ut of alpha. Therefore, cu of t1 alpha is same as cu of t1 of alpha. And this is true for every alpha belongs to V. This implies cu t1 is equal to cu t1 of, okay. This is our lemma. Okay. Now there is another note. The vector space LVV together with the operation composition. This composition we have already defined ut of alpha equal to u of t of alpha. This is called composition. This composition LVV together with this composition is known as linear algebra with identity. Okay.